Good day and welcome back for the second part of our discussion on maximum and minimum values, working towards the idea of optimizing a function. So in our previous video, we introduced the concept of what we mean by absolute max and min. Essentially, that's just where a function will assume its largest or smallest value. And this leads us to a very interesting and a very natural question. If we give you a function in some interval or domain where it is defined, does the function always have to have an absolute maximum and minimum? And this is something where I actually want you to pause the video and give yourself 2 or 3 minutes and think about this. Can you draw some graphs that illustrate a function without absolute maximums or minimums on its domain? See what you think. Hopefully at this point you've paused the video and you've put a little bit of thought into this question. Now, during a typical semester when I'm meeting with a class in person, this really leads to a good discussion. And one of the first responses that I'll typically get back from a student is, what about a function like f of x equals 1? And I say, well, what about such a function? So if we were to graph f of x equals 1, does this function have an absolute maximum or absolute minimum? And you might worry about the interval that it's defined. So let's just consider its interval to be the entire real line. Well, it turns out, yeah, it absolutely does. Every single input gives you an output of 1. And that output of 1 is going to be the absolute maximum value, and it's going to be the absolute minimum value. So it's almost kind of a silly example. But no, every single x is the location of an absolute max and an absolute min. So let's maybe modify this slightly then. What if we were to instead maybe look at something like f of x equals x, so a line going through the origin with a slope 1, and let's just not even worry about restricting the domain. Just think over the entire real line. So does this function have an absolute maximum or an absolute minimum? And it turns out the answer is no. So this function, there is no absolute maximum or minimum that occurs on that interval from minus infinity to infinity. And note the intuition when you look at this. I can't graph the function all the way from minus infinity to infinity, so somehow we want to kind of identify an absolute maximum or an absolute minimum, but it doesn't quite work that way. But that does indicate to us what the issue might be. It's that the interval that we have given is just too much. So let's restrict this a bit. So how about we say the function f of x equals x, nice simple function to deal with, and let's just look simply at the interval from minus 1 to 1. So from minus 1 to 1, we have just a portion of that line, so a line segment. And this is something that most definitely has an absolute max and an absolute min. It has an absolute maximum that occurs at the right-hand endpoint of the interval at x equals 1. And it has an absolute minimum that occurs at the left-hand endpoint of that interval, x equals minus 1. We can very clearly see these 2 points on the graph where you have the largest possible output and the smallest possible output. And it turns out the 2 key things we need to guarantee a function has an absolute maximum and minimum is that it is a continuous function on a closed interval. And this leads us into something we call the extreme value theorem. The extreme value theorem is a very important calculus property. I will almost always abbreviate it by EVT. You are more than welcome to do the same on homework and exams. And what it tells us is if we have those key hypotheses satisfied that we just indicated, if f is continuous on a closed interval, then f is going to have an absolute maximum and an absolute minimum value for some c and d in that closed interval from a to b. And let me go ahead and just make a couple observations. So the first thing I want to note is exactly what we saw in our previous example. These extreme values, they can occur at the endpoints of the interval. That's perfectly acceptable. So they can occur at x equals a or x equals b. Think with that example, f of x equals x from -1 to 1, the absolute maximums and minimums, those so-called extreme values, occurred at -1 and +1. The other thing I want to note is that the hypotheses are important. And if we look at the statement of the extreme value theorem, the hypotheses would really correspond to our assumptions. If f is a continuous function on a closed interval. So those are kind of the two key hypotheses. And what I want to do, just to really emphasize this point, is simply by sketching two graphs, show you that if the function is not continuous, then there is no guarantee of having the absolute maximum and minimum values. And similarly, if the interval is not closed, there's also no guarantee. So just really trying to illustrate and emphasize to you that these hypotheses are important. So the first hypothesis I want to investigate is the necessity of continuity. So I'm going to draw the graph of a function on the interval from 0 to 2 that is not continuous. And the function I'm going to draw is as follows. We start off at 1, we kind of increase up to 3, and then I'm going to make a jump discontinuity there. And then we continue on, and I'll let the function be 0 at an input of 2. So there's no problem here in terms of an absolute minimum. That absolute minimum value occurs at the endpoint x equals 2, which we've already observed is perfectly fine. But I am going to say there is no absolute maximum. And intuitively, you might look at this and say, well, of course there is. 3 is the absolute maximum. But note, in order to be that absolute maximum value of 3, you would have to have an input that gives you 3 as an output. And no input goes to 3. So note in this case, this is an example of something which is not continuous. It has that discontinuity at 1. And there is no absolute maximum that occurs on this interval from 0 to 2. So the hypotheses of being continuous are very important. We also need to make sure we're dealing with a closed interval. So if I draw an example of a continuous function, but I'm going to say it's only defined from 0 up to but not including 2. So maybe something like this. And this is a graphical example of a function which is continuous but has no absolute maximum. So note, there is no absolute maximum on the interval going from 0 but not including 2. So when that closed interval hypothesis is not satisfied, there's no guarantee of having an absolute maximum and an absolute minimum. So I realize these are kind of subtler points, but for a mathematics course, it's always interesting to know how important those hypotheses are to a given property. Now, in terms of how we want to use the extreme value theorem, is not only know that absolute maximums and minimums exist, we want a nice procedure as to how we can go about finding them. So I have a graph to the left. And note, this is a graph of a function y equals f of x. It is continuous on the closed interval from a to e. And because it's continuous on the closed interval from a to e, we can apply the extreme value theorem. And what the extreme value theorem tells us is that there will be an absolute maximum and an absolute minimum that occur in this interval. And purely by inspection, as we noted to start our previous video, we can see exactly where those are. You have this absolute minimum value that occurs in this valley at x equals d, and this absolute maximum value that occurs all the way over at that right-hand endpoint, E. And we want to know what are the defining characteristics that might allow us to find where those points occur at. And note there's two possibilities, and we've illustrated them both here. You can have the maximum and minimum values occur at the endpoint of the interval, or a point between. And if you're going to have an absolute maximum or minimum that occurs somewhere in the interval, not at the endpoints, what is the defining characteristic? So it's at a peak or a valley, and if at one of these peaks or valleys you draw the tangent line, note the tangent line is horizontal, which means the derivative at that value is 0. So that absolute maximum and minimum values occur at an endpoint of the interval or at a point where the tangent line is horizontal. And that's familiar to some questions that we've asked previously to find where the tangent line is horizontal. So i.e., this occurs when the derivative is equal to 0. And just to reiterate, by the extreme value theorem, a continuous function on a closed interval will have an absolute maximum and an absolute minimum that occurs somewhere in the interval. And those maximum and minimum values occur at one of two types of points: an endpoint of the interval or a point in between where the tangent line is horizontal. And we will continue this discussion in our next video. So stay tuned and take care.